Okay, 5.2 transformations of sinusoidal functions, part 2. Okay, so let's think now about determining equations for sinusoidal graphs. Okay, so remember this is our general form for transformations of sinusoidal functions. Sinusoidal functions. Okay, let's just a reminder of what each of these values means. A is your amplitude. B is your okay. B is your horizontal stretch, or B is related. I'll say because we have to use that formula. Related to the horizontal stretch factor by the formula 2 pi over absolute value of b. Okay, remember that. C is your horizontal phase shift. Okay, that's the term we use for sinusoidal functions. It's the C value. For all the other functions that we've done when we do transformations, that's our horizontal translation, either left or right. So we call it a phase shift for sinusoidal functions. And then lastly, the fourth possible transformation is our D value, which is our vertical, I don't want to say translation, vertical shift, sorry, vertical shift. This is like our K value, vertical shift up or down. Okay, so that's a quick review of the 4 different parameters of our transformations of sinusoidal functions. Let me read through the instructions for determining equations for sinusoidal graphs. So this is the next step or the evolution in thinking about sinusoidal functions. The previous part, so part 1, we thought about, hey, here's an equation, draw me a graph based on the A, B, C, and D values that you recognize and do the appropriate adjustments for the transformations. Now we're thinking it of in the reverse way, where we think about, hey, here's the graph, write me an equation. Okay, so here's the procedure. Locate the sinusoidal axis or the midline. Its position determines the value of D. That's pretty straightforward. The other way you can think about it, the first thing is use the sinusoidal axis from the graph, or use the formula to determine the amplitude, which gives the value of A. Okay, so we'll go over that definition or the amplitude formula when we do an example. Okay, you can actually interchange 1 and 2. You can start with 2. You can, because for me, it's just as easy to see, hey, where's that symmetrical point, that horizontal reflection point, or when you think about it, the sinusoidal axis. That's easy to pick out. What's also easy to pick out is the max and the min value, which when you use the formula, you can easily get your amplitude or your A value. Okay, so sometimes I like to start with 2 rather than 1, but you can do either one. Okay, number 3, determine the period and the value of B. So count the number of cycles in 2 pi, which gives the value of B, or calculate the period first using the start of the first cycle on the sinusoidal axis that is closest to the y-axis, then solve the equation for B. That is our classic 2 pi over absolute value of B. We'll show you both ways in the next example. Okay, so method 1, method 2. Number 4, the last parameter. Oh, actually, no, second. Yeah, the last parameter. So this is A, B, this is D, and then we're going to end with C. Determine the minimum horizontal phase shift. So locate the start of the first cycle on the sinusoidal axis. So that midline that we figured out in number 1 up here. Okay. When A is greater than 0, then look for the upward swing of the mountain. So when A is greater than 0, look for that upward swing. Here's that phase shift, right? Match it up and then determine what is this phase shift, right? When A is less than 0, look for the downward swing of the valley. So if I start here, okay, there's my starting point. Oops. There's my starting point. If I have a phase shift this way, that's naturally going to shift my graph. It goes like this, it's going to go like this, and then what is this C value? So there's two ways you can think about it, whether you think about it as A is greater than 0 or A is less than 0. Okay, also depends on the way the graphs are presented to you. That was for the sine function. For the cosine function, similar procedure. Locate the start of the first cycle at the maximum point where A is greater than 0. So closest to the y-axis, or the minimum point when A is less than 0. So phase shift. Here's the classic cosine graph. Starts where A equals 1, goes down. Look for that corresponding point on the transform graph, and then read that phase shift. What is that phase shift? What if A is less than 0? Well, cosine's going to start going down like this. Then you're going to look for that phase shift to see where is that corresponding graph going to end up, right? So what is that C value, that phase shift, okay? So once you get your A, B, C, and D values, use this general form. So y equals a sine of theta minus, oops, forgot, a sine of B times theta minus C plus D, or y equals a cosine of B theta minus C plus D. Okay, so that is these two general form of the sinusoidal function. Write the equation after you find your A, B, C, and D values, and then use technology to verify your solution. So you can do that with your graphing calculator, or you'll see me insert some Desmos videos in between to show you in an interactive way, and you can also try this by yourself, or Desmos to verify. Okay. On a test, obviously, if you have time, use the graphing calculator because Desmos will not be available, but Desmos is a wonderful learning tool. It's also free. Okay. All right, let's go try our first example. Sample 1. Determine the equation of the function graph to the right with a minimum horizontal phase shift in the form y equals a sine of b x minus c plus d, where a is greater than 0. So no reflection in the x-axis, right? So we're going to look at a is greater than 0. What is this minimum horizontal phase shift? Just a quick word about that. We know that these are repeating type graphs, right? We want to write this equation in terms of the smallest possible phase shift, because since this is a repeating graph, this C value, there are an infinite number of phase shifts that you can write where you have a valid equation for this. So what this is asking is that I want that one singular equation where I have the minimum horizontal phase shift. So what's the smallest possible C value? Okay, what is the smallest possible C value that will give us the correct equation for this function that we see? So you'll see a lot of problems written with that in mind, right? We want a minimum horizontal phase shift. Okay, so let's keep that in mind. Let's start. Number 1. Okay, remember I said you can do amplitude or the D value first. Let's do the, should we do the D value? Well, I think the D value you can kind of look at and say, well, 0.5. I'll show you the D value first. Okay, and then that max value, right, is positive 1.5. So the difference the absolute difference between this is 2.0. So I either go down by 1 or up by 1. So if this is negative 0.5, negative 0.5 plus 1, that's at positive 0.5, right? So this is my sinusoidal axis, and that is d equals 0.5. That's one way to think about it, right? To me, that's, well, you can do that. I think that's a bit, it's not that difficult, but it's a bit too much calculation and work. I just think of it this way. Because the max value is super easy for me to read, right? So I'm going to start with calculating the amplitude first. Again, you can start with the d value, like I showed you before, but let me start with the amplitude. That is A equals, we know this formula, max minus the min divided by 2. Here's the max, 1.5. Here's the min, negative 0.5. So A equals 1.5 minus negative 0.5 divided by 2. So my A value equals 1.5 minus negative 0.5 is 2 divided by 2, and my amplitude is just 1. Okay? So that's one parameter done. A equals 1. Oops. Number 2. Okay? Let's calculate the d value, or let's think about our sinusoidal axis. Okay? That's exactly at the halfway point. And you could, again, read it off as this, right? That's one way. And that is y equals 0.5. Oh, let me write that a bit neater, folks. Y equals 0.5. And that is my sinusoidal axis. I can just see that by inspection. But let's use that equation. Remember this equation? The max value equals d plus the absolute value of a. This should make sense. If I want the maximum value, I take the d value, which is my midpoint, and I add 1/2, or I add the absolute value of the amplitude. I know the amplitude is 1, right? Right here. And I know the max value is 1.5. This is the algebraic way to do it. D plus amplitude, either negative 0.5 or 1.5. Oops, sorry. It's 1. Yeah. Sorry about that. A value of 1, so absolute value of 1. So that is 1.5 equals d plus 1, and 1.0. Oops. Oh, math, come on. 1.5 minus 1 is 0.5, and that is my d value. So there we go. So we did it by inspection, and we did it algebraically. Okay, so that's 2 of my values. So I have the a and the d value. Let's think about the b value. Okay. Number 3. Oops. Number 3. Let's calculate the b value. So the horizontal stretch about the y-axis. Okay, let's think about that. So when we think about the b value, I gotta think period, right? So period is one full cycle. So in blue here, folks, pick a starting point. I usually pick a starting point on the sinusoidal axis. Okay, so I'm going to call this point A. Make it easy. I pick the sinusoidal axis versus, like, you can start here, but then where does it end on the other side, right? If I pick something on the sinusoidal axis, I have to end on the sinusoidal axis here. That's one full cycle. I'm going to label that as point B. This is why I use the sinusoidal axis when I'm thinking about my B value. Okay, so let's take a look at this. So in blue again, what is the period? Okay, so what is the period? If I look down here, folks, okay, be careful here. I have pi over 6, pi over 3. Okay, but what is every tick mark, every unit? This is pi over 12. 2 pi over 12. 3 pi over 12. And it should make sense. This is 4 pi over 12, or otherwise known as pi over 3. Okay, so be careful when you're reading the theta values or the x values going across on the x-axis. Okay, so I know that every unit is pi over 12 units. If I start at A and I have pi over 12 units, folks, right here. Okay, if I start at A and I have pi over 12 units, where do I end up for a full cycle? So let's take a look at a full cycle. I go all the way down here, dot, 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 dot. Okay, I said every tick mark is pi over 12. So if pi is 12 pi over 12, this must be 13 pi over 12. Okay, so from A to B, so let's recap this. So you saw it on the graph. From A to B, I go from the period is 13 pi divided by 12 minus pi divided by 12. Well, that's a nice and easy number, 12 pi divided by 12, or just pi. So the period of this transformed graph is pi. But what is the b value? Remember, the b value is related to this. So remember this. Okay, so let's period equals 2 pi over the absolute value of b. Remember that? Okay, so if my period here is pi equals 2 pi divided by b, absolute value b, what's our math here? So b equals 2 pi divided by pi. So my b value is just 2. Okay, so there's our b value. Nice and easy. Okay, another way to think about it is, let me label point C. So this is still on the b value. Let's label point C right here on the sinusoidal axis. So right here. To go from A to B to C. So here's a recap here. From A to B to C, that is a 2 pi distance, right? That's 2 pi, right? This is 2 cycles of the transformed graph, okay? Therefore, b equals 2. That's another quick way to think about it. That's that second way. So if I go back here, right, count the number of cycles in 2 pi, which gives the value of b. That's the quick way to do it. And we showed it right there. I prefer this method. I just like more certainty, and I like the algebraic approach, okay? And then this also forces you to graph read. Okay, number 4. Last part, right? So I have my a value. Oops. I have my a value. I have my b value. I have my d value. What are we missing, folks? I'm missing my c value, my horizontal phase shift. Okay, so let's take a look at horizontal phase shift. Number 4. Okay, I'm going to label, let's see. I'm going to label right here. Let me zoom in so it's completely obvious what I'm looking at here. I'm going to label right on, let's do this in purple, no, green, no, purple, let me choose purple. So I'm going to label this point right here, and I'm going to call it point K. Okay, so let me zoom back out. Okay. So look at point K. From K to A, so this jump right here. So let me highlight it here. From K to A, so this small little jump right here. Okay, look at point K to A. Point K to A. Okay, let's look at point K to A. What do we see? Okay, look at point K. From K to A, this is a horizontal phase shift of how many units, right? So if I imagine this transform graph here shifted to the left, right? That would be our original sine function just vertically translated up, right? So if I think of that shift from K to A, that's my horizontal shift C value. So what is that? This point right here, that's pi over 12 units, so pi over 12 radians. So let's finish our sentence. Look at point K. From K to A, this is a horizontal phase shift of pi over 12 units. Well, which way? Units right. Okay, so that tells me my C value is positive pi over 12. Okay, now we got all our values. So let me put this in a box. Okay, and then let's step back here and take a look. I have my A value, I have my D value, I have my B value, and now I have my C value. Okay, so let me write all of that. Let's do it in red, sure. Okay, A equals 1, B equals 2, C equals pi over 12, and D equals 0.5. I want my equation to take the form of our sinusoidal function, our general sinusoidal function. This, it says, write it in the form y equals a sine of b times x minus c plus d, where a is greater than 0. So I have all four of my transformation parameters, so I'm going to use the general form y equals a sine of b times x minus c plus d, where a is greater than 0. So let's plug all our values in. Y equals 1 sine of 2 times x minus pi over 12 plus, what's going on? Sorry about that. Minus pi over 12 plus 0.5, or let's use exact values, plus 1/2. Okay, so there's our equation right here. So let me put a big old box around it right there. There it is. Okay. There's a second part to this, part B. Actually, there's three parts to it. State the equation of the same function in the form y equals a cosine of b x minus c plus d, where a is greater than 0. Use a minimum horizontal phase shift. Okay, so originally we had y equals sine of x. Then we transformed it to y equals 1 sine of 2 times x minus pi over 12 plus 1/2. Now it's asking, let's write it in the form y equals a cosine of b x minus c plus d. Okay, so let's go back to our graph. I'm going to label another point here. Let's do this in green here. Minimum phase shift, okay? I'm going to call this point T. Let's call that point T. How far was this shifted over? Because if I think about this maximum point and I bring it back to this point, this is where the cosine, so remember the cosine function, when we think about the y-axis as a reference point, the cosine function for the y-axis, it's a maximum point whenever we think of the cosine function, right? So that's why I'm taking the maximum point of this graph. Okay, so this is our maximum point. And if I go backwards to the y-axis, that is my c value. Okay, so let's write this out. This is the way I'm going to think about it because I'm thinking in terms of cosine now. Okay, so let's see here. Point T. So point T above was moved. How many units? What is this from the y-axis, right? From the 0 point. That's exactly pi over 3 units. So if you imagine the cosine function was like this, right? And then it's moved pi over 3 units that way. Okay, so point T was moved pi over 3 units. Which way? To the right. Okay, and I'll say this, to the right from where cosine of x started. Okay, so my c value, if I'm moving to the right, is positive pi over 3. My a value is unchanged, amplitude is still 1. My b value, related to my horizontal stretch, is still 2. And then my sinusoidal axis, I haven't messed with that, so it's 0.5, right? So if I plug this in, y equals 1 sine of 2 times x minus pi over 12 plus 1/2. That transforms into y equals, my a value is still 1, cosine, my b value is still 2, and then x, well, I have to translate the cosine function 3 units to the, pi over 3 units to the right. So it's minus pi over 3. And then that's still plus 1/2. Okay, so this is my same transform function, but written in terms of cosine. Okay, there it is. Okay. Okay, one more part here. Let's think of it in another way, okay? So state the equation of the same function for both sine and cosine. When a is less than 0, use a minimum horizontal phase shift. Okay, so let's think of it this way. So first of all, let's look at our max and min values, right? So our max values, right? How many units apart are they? So, okay. So if I go from, let's say, um, let's label this, I'm gonna, in purple, this one, I'm gonna call this W. Okay, so that's point W. So how do we read this? So X values for max and I should say for successive. So in a row, right? Successive, max and min values. How far apart are they? Are pi over 2 radians apart. Okay. We're thinking about a is less than 0. Okay. When a is less than 0, max and min positions are reflected or flipped, right? Are flipped to points, and this is about the sinusoidal axis, not the x-axis, okay? So it's flipped to points T prime and W prime. Let me label that on the graph. So when A is less than 0, max and min positions are reflected to points T prime and W prime. So we know what that looks like here. So if I look from here, let me just make a little bit more room, folks, here. I'm going to erase some of this. Okay. Okay. When I flip the T value, let me put this in red. Okay, here's my sinusoidal axis. Okay, and then here's my min point. So this is where T prime goes. So T prime. Okay, that's T prime when it flips, right? And that should make sense, right, folks? So all the way down. Okay. For W prime, when that flips, when A is less than 0, what happens here? So let's go to that. Okay, so if I'm looking here, this W value is going to flip all the way to the other side, equidistant from the sinusoidal axis, right? So right here, this is W prime. Okay, if I draw a nice smooth curve here, actually, let me use the okay, so if I draw this, oops, I want to use that. Let's do that. Okay, so when I draw this, let me do it in purple. Yeah, there we go. Okay, so when I draw this, this is what it will look like. Okay, and then if I'm to continue it, let's see if I can do this nice and neat. Okay, something like that, and so on, right? So this is what it looks like. Okay, and then let's continue it this way. Hopefully it's not too busy looking, but you get the idea. Okay, so when I flip it, I just pick T prime and W prime as 2 points that are flipped from the original graph where we have points T and W. Okay, so let's go back and let's finish this up here. Okay, let me write this out, then I'll show you. And then of course I'm going to do a Desmos because the graph is getting, the problem with doing these types of drawing graphs is that they're static. I can't change things unless I erase it and start over. Then that messes everything up and the sequence is all messed up. So what I'm going to do is let me finish this and then I'll flip right back to Desmos and I'll show you with interactive real-time graphs. Okay, so let me finish the rest of the verbiage on this. Okay. So x values for successive max and min values are pi over 2 radians apart. When a is less than 0, max and min positions are reflected or flipped to the points t prime and w prime. Okay? After making a less than 0, so we're reflecting, we shift the graph left by how many units? By, should make sense, by pi over 2 units, so that I'll pick W prime. W prime is where the T point used to be. Okay? Or I guess it's still on like where T prime is. Okay? So let's go. Let's take a look. So after making the reflection A is less than 0, we go from where W prime is to where T is. And that's a shift of pi over 2 units left. So let's take a look. So W prime, where is that? W prime right here. Okay, and then we're going to go to T. How many units is that? So what are we talking about here? Let's go there. What is this value? Well, if I look down here, pi over 6 minus, that's pi over 3. So that's 5 pi over 6. So that's 5 pi over 6 minus, well, what is this? That's pi over 3, folks. So that's 2 pi over 6. And that is 3 pi over 6, or pi over 6. Okay? Okay. Oh, sorry. Oh, math. No. Sorry about that. That's pi over 2. Oh, this is a long example. It needs to be done here. Let's see. Sorry, folks. That's pi over 2. Okay? All right, let's finish this up here. So I know I have a phase shift of pi over 2 units to the left. Okay? So if I start with the sine version, so we want both sine and cosine, right? So let me continue here. Okay? If I start with y equals sine of 2 times x minus pi over 12 plus 1/2. Okay? Let me write that a little better. Pi over 12 plus 1/2. I know I'm shifting it to the left by pi over 2 units. That's the key here. left pi over 2 units. Be careful here. Left pi over 2 units, that's a c value equal to negative pi over 12. Okay, so I can think of it this way. Y equals sine, So when a is less than 0, I have a negative 1 value, right? A is equal to negative 1. So there's our a is less than 0. Okay, so it's negative. Negative 1 sine of 2. So all my other values are the same. Okay, all my other values are the same. I'm just doing a horizontal phase shift. So that's x minus pi over 12 minus, right, negative pi over, oh my goodness. The c value, folks, it's negative pi over 2. Sorry about that. Okay, negative pi over 2 plus 1/2. Okay, so that equals y equals negative sine of 2 times x minus pi over 12 plus pi over 2 plus 1/2. Okay, let's combine those. Negative sine of 2 times x minus pi over 12 plus 6 pi over 12. Okay, making equivalent fractions, plus 1/2. Y equals negative sine of 2 times x minus pi over 12 plus 6 pi over 12. That's plus 5 pi over 12 plus 1/2. Okay, and that is our graph, or that is our equation for the sine function when a is less than 0. So I'll say when a is less than 0. Okay, that's the first one. Okay, there it is. All right, cosine. We're going to start from the cosine graph, or sorry, cosine equation right here, this one. Okay, we know that's equivalent to this equation right here. So I'm going to start there. Y equals cosine of 2 times x minus pi over 3 plus 1/2. And then I'm going to apply that a value less than 0, so a less than 0. That gives me that negative 1. And remember, the only thing I'm changing is a horizontal phase shift, my c value of negative pi over 2. So that's negative 1 times cosine, negative 1 times cosine of 2 times x minus pi over 3 minus negative pi over 2. That's my c value, plus 1/2. Okay, everything else stays the same. The last part here is let's just simplify. So negative, I'm just going to say negative cosine of 2 times x minus pi over 3, x minus pi over 3 plus pi over 2 plus 1/2. Okay, y equals negative cosine. Let's make equivalent fractions. X minus 2 pi over 6 plus 3 pi over 6 plus 1/2. Okay, and then the last part, let's do that last bit of arithmetic. Negative cosine of 2 times x plus pi over 6. So negative 2 pi over 6 plus 3 pi over 6 is plus pi over 6 plus 1/2. Okay, so there is our graph there. Okay, one last bit here. Let me show you all 4 equations. So we generated 4 equations, folks. Okay, 4 separate equations, and they are all the same graph. So let me just go here. We wrote 4 different equations for the same graph, right? So this same graph that we're doing for example 1. So the first one we wrote is y equals sine of 2 times x minus pi over 12 plus 1/2. The second one we wrote in terms of cosine is y equals cosine of 2 times x minus pi over 3 plus 1/2. The third one we wrote is the reflected version of the sine graph, which is y equals negative sine of 2 times x, right here, x plus 5 pi over 12 plus 1/2. And then the last one is the reflected version of the cosine graph, y equals negative cosine of 2 times x plus pi over 6 plus 1/2. All four of these equations, folks, all four of these, believe it or not, are the same graph. Same graph. So you can go ahead and throw this into Desmos or into your graphing calculator, and you will see that you'll get the same looking graph. Okay, so next. Okay, over on Desmos. I love Desmos because I can show you the transformations in real time, and it's a live demonstration, so you can go toggle back and forth between the different states of the transformation, whereas what we just did on the smart board or on a piece of paper is very static. It's hard to erase or go back and forth to see the effect of the various transformations. So let me do it this way. I'm going to start with our sine function. This is our basic sine function where d equals 0, a equals 1, b equals 1, c equals 0. So there's no transformations applied to it. Let me apply the transformations in the order of SRT like we're used to, and let's see if we get our transformation, or let's see if we get the graph that we looked at. Okay, so I'm going to go with SRT, the stretches and the reflect. There's no reflection. A value is 1, right? So A value is 1, so I'm not going to do anything with the A value. That's set. B value is 2. So I have a horizontal stretch which relates to a B value of 2. Okay, so that looks like, if I start with the original sine function, okay, that looks like we are stretching it horizontally about the y-axis by a factor of 1/2, right? So it's gotten thinner by 1/2, right? Okay, so, and the period's actually gone from 2 pi to pi, which, that's a good check. Is that, what do we say the new period is? What is the period of the transform function? It's pi, right? Okay, so that's one way we can prove it. So we did the stretches and reflection. There's no reflections. We did both stretches. Let's do the translations. One of the first things we calculated was the d value, which is the vertical shift, and we said that was 0.5. And that's going to shift it up by 0.5 units. So let's go 0.5. Okay. And then let me do this. I'm going to turn on my sinusoidal axis. Okay, there it is. That's my sinusoidal axis. Good. All right, and then we said the C value, by looking at the graph, we said the C value is horizontal phase shift of pi over 12 units to the right. So C equals positive pi over 12. Let's write it this way. C equals pi divided by 12. Okay. Let me just throw it in exactly right there. Okay, so that's that. All right. Is that our graph that we transform? Well, I'm going to turn on this top one here in red, and sure enough, let me just make it a little bit darker. Let's go 4.0. Okay. So did we do it correctly? Did we read all the A, B, C, and D parameters correctly off the graph? Sure did, because there's our y equals 1 sine of, in brackets, 2 times theta minus pi over 12, close the brackets, plus 0.5. Okay, so there is our transform graph. So we know that the sine function, this graph is written in terms of this sine function right here. So this is our first part, part A. Okay, part B, state the equation of the same function in the form y equals a cosine of b x minus c plus d, where a is greater than 0. Okay, so we looked at this. Let me do this. I'm going to turn this off. Let's keep the sinusoidal axis on. I'm going to look at the cosine function here. What is this? Let me just zero all this out. No phase shift, no vertical translation. A and B equals 0. Okay, so, and let me change the color of this so it's a bit more obvious. Let me go purple. Purple. Well, let me go green. Yeah, green's a good color. Okay. All right. So if I look at what's in green here, folks, okay, that's the cosine function without any transformations applied. Okay, that should look very familiar. Okay, we looked at point T. So if you go back to your notes, point T was a maximum, right? It was moved pi over 3 units from the right. Okay, so again, use a minimum horizontal phase shift. So if I think about my B value, right? A values, first of all, is unchanged. B value, I'm not going to stretch it any different than before, right? So I'm going to keep the same B value, right? Because the B value shouldn't change when I'm going from sine to cosine, right? So the B value is going to be 2. And then what is this phase shift, right? We know that the D value, it shifted up by 0.5. So I'm going to make it at 0.5. Oops, 0.5. Come on. There it is. Okay. So what we are looking at is point T. So point T on our original graph, remember right here. So I'm going to do that. Okay, so I'm going to label that. There's point T. If I look at this point right here, let me fix that. I'm going to label it right there. Come on, label it. Okay, so you see at point T, which is what we drew on our papers, pi over 3 comma 1.5. The green graph is the cosine version of this red graph, but it's pi over 3 units to the left. So to go from here, 0, 1.5 to pi over 3, 1.5, that is obviously a phase shift of pi over 3 units to the right. So when I go back to my cosine graph, let's do a phase shift of pi over 3 units, pi divided by 3 units to the right, and what happens? Bingo, what happens? That green graph is now at the same point now it matches our transform graph, the red graph. So if I just show you for effect, if I reverse the if I reverse the vertical shift, right, and then I go back up, you can see the two graphs match. So the cosine version, okay, is y equals, let me do it this way, the cosine version is y equals, this is 1, the b value is 2, c value is pi divided by 3, okay, and then the d value is 0.5. Okay, so if I'll take that away, and then if I take away the original green cosine graph, and then if I overlay, let's do a different color so I can show you. Let's do it in orange. Okay, all right, so I'm going to overlay this. So if I take away the red graph and I take away the orange graph, there's nothing there. The red graph was our original, that's our transform function. The cosine version of this is right there, and you can see that it's the same. Okay. Okay, folks, we're going to do part C. State the equation of the same function for both sine and cosine, but when a is less than 0. So when we have a reflection, okay, use minimum horizontal phase shift. So let's start with, there's our function. There's the graph of what we initially had. I'm going to put in my sinusoidal axis, okay, y equals 0.5. Let me just bring that up here. And then let's just make it a different color for some contrast, folks. Okay, that is, let's make it blue. Okay, so that's what we're starting with. Okay, remember I had you do that thing where I said label point T and point W and then apply an A value less than 0, so make a reflection. Since it's already translated up to a new sinusoidal axis of y equals 0.5, the reflection is actually occurring around that sinusoidal axis, not the x-axis. Okay, so when I have, I'm going to copy this and let me make a new equation, and then let's unhighlight that. Let me bring that up. Okay, so let's take a look at this. So when I have this, and then let me, that's a line, and I'm gonna go, let's go dotted line, and let's make it purple, orange, and let's make this a little bit thicker. Okay, let's make it 4. Okay, all right, folks. So here's my original graph that I started with in my example. Now, when I reflect it, I'm going to make a value equals -1. So what that looks like is exactly what we'd expect. So if I start with point T, I'm going to label that as T. Okay, and then I'm going to label this value, let's label it as W. Okay, what new points did we create? So this one right here, I'm going to label this as T prime. Okay, T prime, and then this as W prime. Okay, so we asked you to think about the x values for max and min are pi over 2 units apart. So from point T right here, so point T to point W, it's pi over 2 units apart. Okay, when those two positions are flipped to T prime and W prime, they're still pi over 2 units apart. So the trick becomes, how do I get W prime to go back to where T is? How many units is that? So if I go from W prime, that's 5 pi over 6 units, to T, which is pi over 3, so that's 5 pi over 6 minus 2 pi over 6, that's 3 pi over 6, or pi over 2 units to the left. Okay, so if I do pi over 2 units to the left, what does that look like? So if I take this part right here, remember I applied my a is less than 1, so again, I'll just show you, right? -1. Now, I have to shift it over minus negative, so pi over 2 units to the left. That means the c value is negative pi over 2. So negative pi divided by 2. And when I do that, I close those brackets. And you can see that the two transformations line up. The other way to think about it is, remember, let's erase all of this, right? We said the end result was what? 5 pi over 12. Okay, that's from our notes. So 5 pi divided by 12. Hang on. That's pi divided by 12. Minus, oops, plus, oh, okay. So in our notes, it's theta plus 5 pi divided by 12. And once I do that, this is exactly what we had for the negative a version here, right here. If we phase shift it, pi over 2 units to the left, I get theta plus 5 pi over 12 inside the brackets, and I end up matching our sine function. Okay, so that's the sine value. Let's get rid of this. I'm going to keep my sinusoidal axis. Okay, let's get rid of that. Okay, let's bring the cosine up here. Okay, cosine, if I start with c value 0, okay, remember our cosine equation, the original that we found was 1 times cosine of 2 times theta minus pi over 3, okay, with a sinusoidal axis at 0.5, right? So if I do this, right, let's say that's 1. I'm going to match all these folks. That's 2. That is pi divided by 3. And that is a d value of 0.5. Okay, so you can see that they match, right? So if I turn it on, make that a different color here, folks. Let's make that purple. Ooh, well, let's make it green. Green dotted. Yeah, there we go. Okay. All right. So there's our transform function. Okay. Let me get rid of. Let me get rid of all these points, folks. Okay. I'm going to turn on the cosine function here. Remember, this is the same. So this is the same as what's written up here, same. And then for an a value of negative, a negative a value, so a is less than 0, so a equals -1, you can see that it's reflected across the sinusoidal axis. What phase shift do I have to make the two graphs match, right? Remember, we're changing the a values to -1, and then the b value and the d value stay the same. So we're looking at the horizontal phase shift, right? And same sort of deal. If I look maximum to maximum, how do I get those two to line up? Well, it's a pi over 2 phase shift. So I'm doing this. So subtracting pi divided by 2, and you can see that they line up. Or in the end, when I do my math and the arithmetic, I get theta plus pi over 6. Okay, so theta plus pi over 6. So plus pi divided by 6. Okay, and you can see that they line up. So There's the original graph written in terms of cosine. When I reflect it with a -1, it ends up lining up. Okay, so if I take away the reflection, there it is, and then if I put it back in, that phase shift is making the two graphs line up.